In this video, we're going to look at the idea of differentiability, or the question of whether a derivative for a function exists. We start off with the definition and that idea of looking at a function, picking 2 points on it, calling that interval, in this case here, delta x or h. H is the more generic term frequently used in math textbooks. And what we're going to do is let that interval get smaller and smaller. So we get 2 points that are closer and closer together. And in the limit, that is going to give us the slope of a tangent line to the curve. In terms of notation, we can see it as a ratio of delta f over delta x. That very clearly indicates that we're talking about slopes, and then we're asking the question, what happens to those slopes as the interval gets smaller and smaller? In terms of derivative notation, this notation here indicates the derivative of f, the function f, with respect to x. That's what all those symbols mean together. There's a slight distinction made between that notation and this notation here. In fact, let me put parentheses around the first part. This is a verb. The d over dx, without the f in it, translates to take the derivative of. And then we have to have something that it goes beside it to be able to take the derivative of. So this says take the derivative of f with respect to x. This notation is very handy if there's some very complicated function we want to look at. This is a reminder, or again, a verb or a transformation that says, in a minute, I'm going to take the derivative of what's beside me. Last but not least, there's also the notation of the prime, which indicates one derivative. Typically, physicists sometimes use dots, and we're going to use single primes, double primes for 2 derivatives, and so on. With all that notation in mind, all these variations on the theme, from the definition to the shorthands, now we return to the question of what does it mean for a function to be differentiable? The informal definition is given here. If we pick a point A on the function, so imagine we go to some coordinate A, the graph is doing something, we say that it is differentiable there if there's a derivative of at A, which means that this limit here exists. Graphically, a little more intuitive is having a unique and finite slope at the point. We'll look at some counterexamples in a second. Since that slope is the slope of the tangent line, another way we can say is that f is differentiable at A, let's include the point, if its graph has a non-vertical tangent, if it makes sense to define a single tangent line at that point. There is some fine print here that the graph cannot be vertical. Why do we include that one special case? Because a vertical line does not have a finite slope. If we talk about a line that's up and down, we could say the slope is either undefined, or some might call it infinitely large, depending on how we get there. So a pure vertical line on an axis is not something that would have a slope. Let's explore the ways in which a function can fail to be, so problem points for a function, fail to be differentiable. The first one is a function that's not continuous. So if we look at that, if we have our function continuing here, but then it jumps down to here, even if we have a filled in dot, the issue there is tangent to which part of the graph. There's no easy way to define a single tangent line because the function isn't uniquely defined at the point. So that is not differentiable. Sometimes the function can be behaving quite nicely and actually still be continuous, but if it takes a turn and we have a conflict or an ambiguity with 2 different slope lines, this is what we'd call a cusp, there again we can't talk about a single derivative, so it would be not differentiable at that point. The third possibility that we frequently encounter is one we saw on the last page, where the function continues on, fine, has well-defined slopes, is continuous, doesn't have a cusp, but for just an instant, the tangent line at some instant is purely vertical. So if we drew a tangent line to the graph as it transitions here, it would be pure vertical, and that has an infinite slope. We would also say that the derivative is undefined there, not because we can't draw a tangent, but because we can't put a number or a finite number to the slope line.